collaboration with a lot of experts, some of which are present in this room, and also a lot of undergraduate researchers that are collaborating with us at UMKC. I'm a fourth-year PhD student with Dan McIntosh at University of Missouri, Kansas City. So let me start off by saying that I'm really interested in understanding the role of galaxy mergers in the grand picture of galaxy evolution itself, and especially I'm trying to connect the dots between what happens during the merging process and how do galaxy merging influence the transformation and growth of galaxies in the universe. So there's empirically, observers try to identify mergers primarily using two different observational techniques. One is called as the close pair method, where the idea is to select galaxies in close physical proximity as plausible merging systems. And there's a lot of work that's happening in the recent years, and also the research dates back many decades. And in this talk, I'm going to focus on another technique which is also used in the empirical observations, which is tidal features. So tidal features are these really transient and interesting features that galaxy mergers exhibit during their interaction with the nearby companion. In this talk, I'm going to focus and I'm going to show some preliminary results and preliminary work towards identifying tidal features and essentially trying to connect galaxy and galaxy evolution and galaxy merging picture. So in order to do that, I'm using the data set that is produced by the CANDLES collaboration. And CANDLES is one of the largest HST time allocation surveys which observed 5 different regions of the sky and produced rich data sets for the scientific community. And especially, I'm using the structural parameter fits that were produced by Arjen van der Wal in 2012 for the CANDLES sample. And so here I'm trying to visualize what that data looks like. So for example, Arjen in 2012 produced the structural fitting, meaning using a single Sersic profile fitting using popular light profile fitting tool called as GalFit. And here's an original image. I'm going to refer to these words throughout my talk. So the original image and the model image for that particular galaxy, and then the model subtracted, which we call the residual image. And specifically throughout my talk, I'm going to analyze the structure that the galaxy exhibits in the residual images. And that's why my title is called as Analyzing the Residual Structures. Okay? So these, we are leading an effort at UMKC to visually characterize different types of residual structures hosted by these massive CANDLES galaxies over a redshift range of 1 to 3, among which a lot of people here are also involved with. So what I'm going to do is I'm going to emphasize the structure extraction in residual images for a sample of 16 galaxies that host different kinds of residual features shown in this table in column 6. So you can see here some galaxies host a spiral-like structure. Some galaxies have a 2-component disk-like structure that are visually identified as hosting those features, and some of them are plausibly tidal features. So I'm going to show the extraction for those galaxies in my demonstration. So let's take an example galaxy from my 16 galaxy sample. So here I have a 10 to the 10 solar mass galaxy at redshift of 1, and I show this source extraction segmentation regions overlaid on each of the object. And I'm also showing the corresponding residual image on the right-hand side panel over there. Okay? So in order to extract the features that are present in these residual images, what I'm going to do is I'm going to first start with the smooth residual image with a boxcar filter to boost any underlying faint signatures. And also, you can see I overlaid some of the segmentation contours, and also I'm showing 2 different circles here. I'm masking anything out inside that central region, and I'm only considering the region in between these 2 circles here, and I'm masking out any known sources that we identify. Okay? Why am I doing that? This conceptually shows that I'm only trying to extract features in the close proximity of the galaxy. Okay? Now the next step is I'm showing the sky background distribution first, and then I'm showing the red histogram, which is the region of considerance, the pixel distribution that we consider in this unmasked region of the image. And what I'm going to do is I'm going to emphasize this a threshold, which is the 2 sigma threshold represented by the vertical blue line. And what I'm going to do is I'm going to select all these pixels that are outliers, essentially. And when you visualize that, it looks like that. So, and here the color coding represents the unique contiguity of pixels that are contiguous. And then you see, what we see is we see an obvious feature that shows up that has a large area and a lot of small specks of pixels too. And what we do at this point is we run we calculate what is the expectation of these contiguous regions that happen to show up just by random chance for our particular selection right here. And when you do that, you get an area threshold, which suggests that anything greater than that should be significant above a random expectation. And when we do that exercise and select significant regions, what we get is that. And the extracted feature is overlaid in this red shading, and I quantify the surface brightness of that particular feature. In this example, it looks like an arm-like feature with surface brightness 25.5 magnitudes per square arc second in the H band, which is 1.6 micron on Hubble Space Telescope. Okay, so what if we just apply this method on the 16 galaxies that I had in the table that I previously showed? I have some galaxies that exhibit plausible 2-component model of like a bulge plus disk sort of situation, and I have some spiral structures that are beautiful 2-armed spiral structures that show up. Which is not surprising because we selected them to have different types of structures in their residuals. Now the interesting part is when you go and apply this on galaxies that exhibit plausible tidal features. And here you can see some of the examples that I have are interacting closed pairs. We extract sort of broad extended features, for some of the examples, and we also extract thin tail-like structures. And the goal of this method for me so it's a starting step for me to implement a technique to extract these tidal-like features in hopes to quantifying their shapes and get to a better classification scheme in an automated sense. That is why I'm trying to do this exercise right here. So let me switch gears and tell you what happens if I take the same exact method and apply on mock observations of a known galaxy merger from the Vela simulations, which a lot of recent work has been done on this suite of simulations. And what I do is I use one particular system in this suite of 34 high-res zoom-in galaxies, and I use the mock HST observations of a gas-rich major merger that happens around redshift of 1.5. And I analyze the extraction of residual features as a function of time through the merging process. And what happens if I do that? And I'm just going to visualize what happens there. I do this exercise at 2 different depths, which is one is at Hubble 2 orbit depth, which people often refer to as Candle's wide depth in Candle's collaboration, and then there's 10 orbit depth, which is a deeper observation. And you can see the panels right here are progressing in time as a function of at different merger stages, and the red features that I show are the extracted features as a function of time. And you can see right after the coalescence stage, the tidal arm starts to develop, and it's really interesting to see at this stage the tidal feature sort of becomes extended and then starts forming clumps-like structures inside the feature itself, which dissipates the arm-looking structure there, which is really interesting to me. So one thing in the last few minutes I'm going to talk about is some of the work that my undergraduates are doing with respect to this particular technique. Is that Logan Fries is one of the undergraduates who's trying to extend the method that I just demonstrated to mergers in the Sloan Digital Sky Survey with hopes to extracting these features at multiple wavelengths and understanding physical properties of these tidal features such as color and stellar mass on a sort of a semi-resolved fashion using the Voronoi-Binning sort of approach that we've seen in the previous talks. And this work is similar to some of the works that is being done by Alex de la Vega and Maaz Diaz-Jafarziani. And also, this work is also similar to the work done by our next speaker. So I think it will be really interesting to do this and compare to other methods in the literature. And finally, I just want to talk about one additional project that another undergrad is trying to do, is to understand the structural similarity of tidal features in candles. You can see these two are interacting closed pair systems, and I'm really intrigued by the fact that they show very similar features. And this is a merger that's happening at a redshift of 2. This is happening at redshift of 1. And also, here's a merger that is selected from candles. Here's a galaxy selected from the candle survey, and this is one of my snapshots of a galaxy merger at a particular time step that shows visually similar morphologies. What it's trying to do is trying to quantify the similarity of structures across cosmic time with hopes to understanding what kind of mergers create what kind of features. That's the goal. This is in a the project is still in an infancy stage. I'm happy to talk to you about any ideas you might have trying to implement that. So I'm just going to leave out the summary slide. 3 important aspects that I want you to take away from my talk is that I showed I demonstrated the feature extraction technique in the candles dataset. I applied it to a known galaxy merger inside the simulation. And I have demonstrated a couple of projects that the undergraduates at UMKC are trying to do with respect to the method that I demonstrated. Thank you.
Sure.
So if you want to convert these to measure rates, so you're going to need a large scale, like tidal features, and convert these to measure rates.
Mm-hmm.
At some point, you need to calibrate what the observability of these tidal features and how long, what they tell you of when the merger takes place.
Yeah, so this is something that I want to do on a grand scheme after I implement this method and apply it on a large suite of simulations. And here's the I quantify the surface brightness of these features that occur at different time steps. I want to look at what is the time scale during which the tidal features appear during the merging process. And that is actually my primary thesis goal, is to constrain the time scales both in closed pairs and also tidal features. So yes, that's definitely on my plate.
Do we have another question? Sure, David.
Yes, I'm wondering, how do you separate between spiral features that are actually a result of minor mergers, for example, compared to maybe symmetric? How do you do this quantitatively or by eye, or how do you?
So right now it's by eye, but the hope is to extend and quantify their shapes to see any deviance from let's say spiral. Like there's some aspect of spiral features that is same, and then for tidal features something else might be different. We want to quantitatively sort of separate out these features, and the end goal of this whole exercise is to identify tidal features apart from all other known signatures. That's the goal. Right now it's only by eye, but I'm trying to move towards quantitative differentiation of features.
So I'll take a question if no one else will. Have you thought about using neural nets or AI or something like that to identify features?
So that's a goal in in the ongoing projects that we have, but I've definitely thought about it, but I have not thought about it enough to fully comment on the path. I haven't seen it all the way through, so I cannot comment fully.
Let's thank the speaker again. And now we have Erin Cato Fong, who's going to continue telling us about tidal features.